Hello, everyone. Welcome back. Today, I'm going to use one example to show some concepts in bivariate random variables. There are joint PDF, marginal PDFs, conditional PDFs, and then some two other concepts, covariance and correlation. It's going to be a little bit tedious because we have a lot of algebra, but I hope that the video would clarify certain these concepts. Okay, so what is joint PDF? Joint PDF is it's called joint probability density function for two variables, those bivariate. PDF means it's the function that we can use to find probability. The definition of a PDF. So suppose we have two random variables. Say they have a joint PDF. What it really means is that for any set, say A, capital A, is a subset of R2 X, capital X, Y, in this A, so you have a probability of that. So probability that the joint the joint random variables, a pair of random variables X, Y in that set A can be expressed by the integral of this probability density function. Here actually it's a double integral, okay? So for example, if we want to calculate the probability of X greater than or equal to A, less than or equal to B, and then capital Y greater than or equal to C, less than or equal to D, then we can have the double integral of this joint PDF dx dy. Okay, be careful with the lower limits, upper limits corresponding to X and Y. Okay. It's different. It's slightly different from the discrete case. The discrete case, the joint PMF. The joint PMF really is the probability. So suppose we have a joint PMF. We have a f of X. A y, and then it's just the probability of capital X equaling little x and capital Y equaling little y. But in a continuous case, for any little x, little y, two values, so in continuous case, the probability of x equaling little x, capital Y equaling little y is always 0. So little f of x, y here in continuous case, it's really not the probability themselves. I mean itself. So it's not the same as the probability of capital X equaling little x, capital Y equaling little y. Okay. It's a density function, so you can use this function to find the probability. Okay, so that's a sort of difference between the PMF and the PDF. All right, so let's look at this example. We have a joint PDF, f of xy equals c times 2x plus y, where x is greater than or equal to 0, y is greater than or equal to 0, less than or equal to 1, both less than or equal to 1. So the region is sort of a square. It's rectangular shape, and the problem gets easier. Okay, so the first task is to find little c. Using the fact that it's a PDF, so if you integrate the joint PDF on R2, you'll get 1. Okay, that's the one of the properties of a PDF or joint PDF. So we're going to use that to find little c. So I have 1 equals, let's do the double integral from negative infinity to infinity, and then you plug in, well, you put fx, y, and dx, dy here. This is a definition. I mean, it's a property of a joint density, so joint PDF. So it doesn't really matter what f is, what kind of a function f is, as long as it's a joint PDF, you would get this equation. Now, what I want you to pay a little bit more attention is that when you plug in this function c times 2x plus y, you really need to change the lower limit and upper limit for both x, y from 0 to 1, from 0 to 1. Okay, you cannot keep negative infinity and infinity for the integrals. All right, now when we integrate this function with respect to x, we're going to treat y as a constant. So let's find the antiderivative. C is just a constant. Dx, right? 2x dx, so antiderivative is x squared. And then you have y is a constant, so y times x. And then you evaluate from x from 0 to 1 dy. The problem is a little bit simple in the sense that when I plug in 0, it's just 0. All right, that's deliberate. The calculation would be easier. So when x equals 0, it's 0. So when x equals 1, you get c times 1 plus y dy from 0 to 1. And then you find the antiderivative of this function with respect to y. You have c times y plus c times, you can move out c, but that's okay. C times the antiderivative of y is half of y squared. And then you value from 0 to 1, you plug in 1. I think it should move out c. So you have 1 plus 1/2. Okay, you plug in 0 to 0, so it's just that. So we have c times 3/2. I get c equals 2/3. All right, so that's the way to find c. Now, I'm going to just replace this c by 2/3, okay? And then we work on the other things. All right, let's work with the marginal PDFs. There are two marginal PDFs. Let's denote them by f subcapital X of little x. So this is the marginal density of capital X. That is the integral from negative infinity to infinity. And you have a joint PDF and integrated with respect to y. So that's the definition of a marginal PDF for x, and similarly for y. All right, but you're going to integrate it with respect to x. Now, let's work with this example. So the marginal, once you plug in 2/3 times 2x plus y, again, you need to change the lower limit to 0 and upper limit to 1 and integrate with respect to y. Antiderivative of 2x with respect to y, so 2x is just a constant, and then you have y, the antiderivatives have y squared, and y from 0 to 1, 2/3 times, you plug in 1 for y, so you have 2x plus 1/2. Okay. A quick check, that is a PDF. You integrate this function with respect to x, the antiderivative 2/3 times x squared plus half x, and you evaluate from 0 to 1, you do get 1. Okay, very quickly you see 1 plus 1/2 is 3/2. You multiply by 2/3, you get 1. So that's pretty good. I'm pretty sure that is right. It's a marginal density function. Okay, and similarly, we can work with the marginal density of y. That would be the integral from 0 to 1, 2/3 of 2x plus y dx. 2/3. All right, so 2x, entire derivative is x squared. And for y, the entire derivative of x with respect to x is y times x. And then x runs from 0 to 1. Yeah, 2/3 times 1 plus y. Okay. And similarly, you integrate with respect to x. Sorry, integrate with respect to y. You have y plus half y squared. And then you go from 0 to 1, you will get 3 halves again. So I do get the marginal density. All right, so I'm going to copy these marginal densities here. So f x little x that equals 2/3 times 2x plus 1/2. And then I have marginal density for y, which is 2/3 times 1 plus y. Again, we still have x greater than or equal to 0, less than or equal to 1. And here y is greater than or equal to 0, less than or equal to 1. Okay. Now let's work with conditional PDFs. And for bivariate random variables, we do have 2 of them. So f x given y. Different textbooks may have different notations. This is the notation I use. This is to denote that it's the conditional density of x given y, but then you have 2 independent variables x, y. It's defined to be the joint density divided by the marginal density of y. Okay, and similarly, you have this conditional density. Again, it's the joint density divided by the marginal density of x. So we simply plug in these functions, and we would get the conditional density. Fx is 2/3, 2x plus 1/2. So that's 2x plus y over 2x plus half. All right. And it's a little bit tedious to check that this function is a density function. We can check some of them. One of them, for example, the conditional density of y given x. Let's say x equals half. Okay? X equals half. And you have y here. So you basically plug in half for x in this expression. So you have 1 plus y, 2 times x is 1, and 2 times x is 1 plus 1/2. That is 2/3 times 1 plus y, which is actually the same as the fy, the marginal density of y. But this kind of coefficient, it's a coincidence. You have x equaling 1/2. It happens to be like that. If you plug in x to be 1/4, then it will be different from the marginal density of y. Okay, so and similarly, we have this conditional density. You have 2/3 of 2x plus y. So that is the joint PDF, and then we have the marginal with respect to y plus y. So I have 2x plus y over 1 plus y. Again, both x, y are greater than or equal to 0, less than or equal to 1. Okay, so for continuous case, the conditional PDFs are pretty easy to find. Once you get the marginal and the joint density is given, then you just find the ratio. So it's pretty easy. The conditional PDFs are done. We're not going to use them for the following concepts. So I'm going to just erase everything here. Let's define the covariance. So the covariance of two random variables that's defined to be E expectation of X minus mu of X. So it's the mean of X, and then you have a Y minus mu sub Y. So it's a cross product, and you take expectation of that. Now, if you expand it, if you expand the cross product, and then you use the property of expectation, you would get this. It's the same thing. Normally, when we use hand to calculate covariance, this formula is probably more convenient to use, and so I'm going to use that. Okay, so let's find E of xy first. E x times y, expectation of x times y. That's according to the definition. So let me write down the definition first. You have an integral of xy times the joint PDF and dx dy. So that's definition. Well, maybe it's a property or theorem about a function of random variables, expectation of a function of random variables. Anyway, let's plug in the joint density, and then I'm gonna replace the lower limit, upper limit to 0 and 1, xy at 2/3 of times 2x plus y dx dy. It doesn't really matter which integral you wanted to integrate first for this problem, but sometimes actually one direction is better than the other. But this one, it doesn't matter. So let's integrate this function with respect to x. Okay, maybe I do one more step. So 2/3 times y, I'm going to multiply, to put x inside. You have 2x squared plus x times y. And then you have a dx dy. And then, oh, hold on a second. I still have that integral here. And then the inside 2/3 of y, the entire derivative of this function with respect to x. You have 2/3 of x to the third plus 1/2 x squared times y. And x runs from 0 to 1 outside dy. Integral from 0 to 1, 2/3 times y. By plugging 1 for x, you get 2/3 plus 1/2 y and dy. All right. And then let's move y inside. I have 2/3 of y plus 1/2 of y squared dy, and find the entire derivative. You have 2/3 times 1/2 y squared plus 1/2 times 1/3 y to the third, and y runs from 0 to 1. You have 2/3, and then you have 1/3 here plus 1/6. 2/3 times, what is this one? That's 1/2. So it's just 1/3. All right, so we have a e of x times y to be 1/3. Okay. Well, I just did it. I didn't really prepare for, I didn't calculate earlier, so I hope it is right. All right. Let's work with mu of x. This is the expectation of x. Now, when we talk about the joint PDF and we calculate mu of x, actually, you're going to consider x as capital X as a function of capital X, capital Y. So it's like a projection from R2 to R1. According to the theorem, again, it should be actually the double integral of x times the joint PDF, and then you have a dx dy or dy dx. It doesn't really matter. It's negative infinity to infinity and negative infinity to infinity. And then you're going to switch the order dy dx. And when you integrate with respect to y, x is a constant, you move it out. Then you have the integral of fxy dy. And that actually is just the marginal density of y. So, sorry, marginal density of x. So it is really just the integral of x times the marginal density of x. That is consistent with a univariate situation, right? It's just the density of x, and then you have an expectation of x. So we're going to use that, use the marginal density, because it's kind of easier to work with for the moment. So we're gonna change the lower limit, upper limit. You have x times the marginal is here. You have a 2/3 times 2x plus 1/2 dx. So you have a 2/3. You have 2x squared plus half of x integral and dx, find the entire derivative, 2/3 times 2/3 x to the third plus 1/4 times x squared, because entire derivative of x is 1/2 x squared, and then 1/2 is 1/4 x from 0 to 1. You have 2/3 times 2/3 plus 1/4. What is that? That is 2/3 times, let's say 12 here, and 8 plus 3, you got 11. You cancel out 2, you have 6, you have 18 here, 11 over 18. So I'm going to put mu sub x equals 11 over 18. All right, that's for mu x. Let's do mu y. Mu y is integral from 0 to 1 y times the marginal density of y, which is 2/3 times 1 plus y. Okay, so just here. And dy, that equals 2/3, the integral from 0 to 1, 2/3. Then, yeah, it's a little bit ugly. So integral from 0 to 1, 2/3 here, put y inside, y plus y squared dy. And that equals 2/3, the entire derivative of y, half y squared, entire derivative of y squared, 1/3 y to the third, and y from 0 to 1. And then you have 2/3 times 1/2 plus 1/3. That's 5/6. That is 10/18. Let's keep it there, 10/18, even though you can simplify it. 5/9. Okay. Okay, now we find the covariance. Okay, covariance equals the expectation of x times y, which is 1/3 minus 11/18 times, let's do 5/9. So I have a G. What is that? So 9 times 18, 162. And I have 54 minus 55. That's negative 1/162. Mu of y equals 10/18, and the covariance of x and y is negative 1/162. Negative means they are sort of negatively correlated. So when x gets bigger, y tends to get smaller, but the value is pretty small. We don't exactly know the strength of a linear relation yet. Well, covariance tells us a linear relation, okay? But it's more appropriate to talk about the correlation, because correlation is a standardized covariance. It has a better meaning, I think. So let's define a correlation. Rho xy. Sometimes we don't need to write xy, so rho. It's defined to be the covariance of x, y divided by the standard deviation of x times the standard deviation of y. Okay. The correlation coefficient, this sometimes is called a correlation coefficient. It's always from -1 to 1. Okay, from -1 to 1. And it tells us the linear relationship. It's a linear relation. When rho is close to 1 or -1, then we say they have a strong linear relation. When rho is positive, that means two random variables are positively correlated, which means when x gets y is bigger, y tends to get bigger. I really cannot say exactly when x gets bigger and y has to be bigger, so we don't really know. It's just it's kind of a trend. And when rho is less than 0, then it's negatively correlated. Okay. When rho equals 0, then they have a 0 correlation, or they are not. The covariance is also 0, so they are uncorrelated. It doesn't really mean that they're independent. Okay, it only says that they don't have a linear relation, or a linear relation is really weak. 0, then you don't have a linear relation. But it doesn't mean they are not related. They may be related by some other types of relation. For example, x squared, y equals x squared. I mean, maybe there's some other relation. Okay. I don't exactly know if it's possible that if y equals x squared, then they have the linear correlation is 0. Maybe we can design certain things. I'm not really sure. But anyway, 0 correlation doesn't mean independence. Okay, and also 0 correlation doesn't mean any causality. All right, you really cannot say one causes the other. It only tells the relation between these two. They're sort of symmetric when we talk about correlation. Okay, so let's in order to find correlation, we need sigma x, sigma of x, sigma of y, standard deviations. That's a little bit tedious, so let's calculate them anyway. All right, so let's use this formula, okay? The variance of x, by definition, is this, e expectation of x minus mu sub x and squared. But expand it, use the property of expectation, we get this formula instead. And I usually like to use this kind of expression. You see e of x squared, and then you have exn squared. Okay, so please pay attention that these two quantities are in general not the same. This is the integral of x squared times fx. This is integral of x times fx, then squared. Okay, so the square, the integral of the square cannot move out the square. The integral is linear, but you cannot move out the square from it. Okay, we're going to use that. We're going to use this formula. So let's find e of x squared. E of x squared integral from 0 to 1, we're going to use the marginal density. Okay, x squared times 2/3 2x plus 1/2 dx. So you let's move out 2/3, and then you have 0 to 1 integral, and you have inside 2x to the third plus half x squared dx, and you have antiderivative 2 times 1/4 times x to the fourth plus 1/2 times 1/3 x to the third, and x from 0 to 1. That's 2/3 times 1/2 plus 1/6. That is 2/3, 2/3, 2/3. You have 4 9s. Okay, 3 plus 1. Okay, let's look at e, well, let's put somewhere. E of x squared equals 4 9s. Okay, variance of y. Hey, I actually didn't finish that yet. So the variance of x is e of x squared minus e of x and squared. That's 11/18 squared. Okay, so I have a 4 9s minus 121, 18 squared, 256. Is that right? I don't remember actually. Let's calculate. No, 4 indeed. 324. Okay, so I have 324, and then 4 times 36. And then you have 121, 144 minus 121. Yeah, it's really tedious. Not liking it, but 23/324. Okay, so sigma of x squared, that's variance, right? That's 23/324. All right. Again, I'm just doing it. It's possible I made some calculation mistake. If you spot anything, you can put in the comment. If it's really bad, terrible, then I probably will re-record it. Otherwise, we'll probably just leave it like that. Okay, so variance of y, e of, no, we wanted to find e of y first, y squared first, e of y squared. E of y squared. And then you have a integral from 0 to 1, you have y squared times the marginal of x of y. G. All right, so you have a 2/3 and the y squared plus y to the third dy, and that is 2/3 times 1/3 of y to the third plus 1/4 y to the fourth. Y from 0 to 1, 2/3, you have 1/3 plus 1/4. So that's 2/3 times 7/12. 7/618. Okay, let me quickly check if I have any obvious mistake that I can spot. Right, I didn't find any. Okay, move on. All right, that is EY squared. So variance of y, that E of y squared, expectation of y squared minus E of y then squared, but we have all these values somewhere here. I have 7/18 minus 10/18 squared. Let's do 5/9 squared. That's 7/18 minus 25/40 of 81. So I have 2 times, so 162. 162, so you have a 9 times 18, that's it. So 30, 63. And then you have a 81, 2, so 15. So I have a 13 out of 162. It's like 26 out of 324. Let's do that. All right, so 1326/324. So like this and this, they have the same denominator, but it's not crucial. It's just my personal preference, I guess. All right, now we're ready for the correlation. So the correlation equals the covariance. And then we have sigma x, which is the square root of 23 out of 324 times square root of 26 out of 324. And then I have a square root of 23 times square root of 26 on the bottom. And -1 out of 162, then you need to multiply by 324. Okay, the square root of 324 multiply together, square it, you get 324. And it's in the bottom of the bottom, so you flip it. I get -2 over square root of 23 times square root of 26. This value is pretty small. I don't have motivation to really calculate it out. I don't want to use a calculator for the moment, but it's pretty easy to figure out this value. So I would say X and Y, they are negatively correlated, and the correlation seems to be, the linear relation should be sort of weak. Okay. All right, so that's the end, sort of end of the video. I used one example to introduce these concepts. Now, in the exam, I normally don't ask people to calculate correlation coefficient using the joint density because it takes a lot of time. But I may ask you to use certain properties to get the correlation coefficient. And if you are able to spot that the joint density tells us that the random variables are independent, then obviously correlation is 0. So you sort of need to see that very quickly. Otherwise, you go through this long journey and probably don't have enough time in the exam. Okay. Oh, that's about it. Oh, thank you for watching.